audio.
And we're going to go look at the analog to digital converter today. And what I want to start with is just the block diagram.
Of course, when we look at these block diagrams, one of our first impressions is always there's more stuff than I want to try and understand, and we kind of shut down when we're looking at it. What I want you to realize is that in the lab this week, we are going to use the A to D converter in its simplest form. What that means is we're not doing interrupts, we're not using any kind of external triggering, we are not using any kind of analog watchdog system, and we are not using what they call injected channels. So if you were to go through the block diagram, you could remove anything to do with the interrupt system, you could remove anything to do with the analog watchdog, you could take out anything that says injected channels or injected data registers, and you could also take off all of this stuff at the bottom, which is our trigger selectors. And what that does is that leaves us with a diagram that shows 16 inputs, 2 internal inputs, a multiplexer, and then one of those signals is going into our A to D converter as what we call a regular channel. And once we've done our conversion, the result of the regular channel appears here in the regular data register. So it becomes a pretty straightforward system. We connect our analog signal to one of the analog inputs. We configure the GPIO port so that that pin is an analog input. That connects it to the multiplexer. We then configure the multiplexer to pass that signal into the A to D. We tell the A to D to take the value of the voltage and turn it into a 12-bit binary number. And when it's done that, it stores that 12-bit binary number up here in this 16-bit register. And we're done. That's the whole thing. Now, because there's so many different functions that could go on, and in some cases there's multiple A to Ds inside your device, when you go and look at the register map for the A to D converter, again, it causes a little bit of anxiety because there are so many registers, and of course, when you look at a subsystem for the first time, you don't really know what any of those registers are for. So let me bring your anxiety level down just a little bit. There are only 4 registers in this entire map that we need today. The default value of all the registers is a good place to start. So we're not going to have to modify very much. The 4 registers that we're going to talk to in the configuration stage, we are going to write to the control register 2, right here. We're going to write the AD on bit. That turns on the A to D converter. That is actually the only part of the A to D converter we need to deal with during configuration or during initialization, is just to turn that bit on. Everything else, by default, is just fine. When it comes time to use the A to D converter, if you follow that sequence of events from the pre-lab, it says you have to start a conversion. To start a conversion, you simply write this bit again. You never actually make it a 0. You just keep writing 1s to it. You write a 1 to it during initialization, that turns the A to D on. It's just not doing anything. You write a 1 to it again, it starts its conversion sequence. Okay? Now, when it starts its conversion sequence, it needs to know which channel it's converting. So before you write that, you have to come down to this register, ADC sequence register 3, and you have to put some value in these bottom 5 bits. Okay, remember, there's 18 possible inputs. So when you look through these sequence registers, you're going to see that it's got sequence 1, sequence 2, and it's going to go all the way, go back to sequence register 1, it goes all the way up to sequence 16. So there's, it's got 16 possible channels that it can convert in a sequence. We're not doing that. We're doing a single conversion. And in a single conversion, it looks here. It looks at what is the first channel that I'm going to do the conversion on. So remember, your inputs come in on, they call it input 0, input 1, input 2, input 3, and so on. We're using PA4. PA4 is analog input 4. So all I have to do is write the value 4 into this register, and that will be the channel that I'm getting my conversion on. If I was using analog input 2, I'd write a 2 in here. If I was using analog input 7, I'd write a 7. That is the channel that I want to get the analog value from. So we come in, we write to sequence register 3 with the channel number that we want. Then we go back and we write a 1 in the 80 on position. That starts the conversion on our selected channel. Now we wait. What are we waiting for? We're waiting for this bit, the EOC bit in the status register, to go high. That tells us that the conversion is complete. If this bit never goes high, we probably did something goofy like forgot to turn on the clock for the A to D system. Okay, so there might be some debugging or troubleshooting. But in normal operation, we're waiting for this bit to go high. And when it goes high, the last step is to go get our data. And where's our data? Our data is sitting, come on. Our data is sitting right here in the ADC data register. It's these 16 bits right here. We can read that as a 32-bit number. We can read it as a 16-bit number. Our data is going to be in the bottom 12 bits. So our data is going to be a number that ranges from 000 up to FFF. Okay? So that's the process of doing A to D conversion. Back to the lab handout. So what are you actually going to do in terms of programming today? You're going to make a library of functions. Probably only 2 functions. Probably one to initialize the ADC and any associated I/O. And then probably another one which will start the ADC and read the result. Okay, so steps B and C can probably be combined into a single function. And you're going to be using PA4 as your input channel. So that's the initialization and the function you're going to call. So you're going to call that function from inside your main loop. Call it, get a digital value equivalent to the voltage that's currently on PA4. So it could be any voltage between 0 and 3.3 volts. And then use those 4 LEDs that you have hooked up to display whether the analog voltage you're reading falls within one of 4 ranges. So you're going to get a value. You're going to have to do some comparison on that value, some analysis of what is the number. And based on that number, you'll turn on indicators to show us is the value between 0 and what would it be, 0 and about 0.825 volts, or is it between 0.825 and 1.65, or is it between, so those are the ranges that would work out. Your VREF is 3.3 volts. So you can calculate what the bounds of those 4 ranges are. And just use the LEDs to show, is your analog value in this range or in this range? Where does it sit? Use the V+ output of your ADLM to generate those voltages on PA4. And again, I can't state this enough times and in bold, right? Don't apply any voltage below 0 or above 3.3. Okay, so keeping the voltage in that range. Run your program, convert the value, show the LED. Now, really, this should be happening on a continuous basis. It should be happening on some regular basis. Maybe you want to do something like use SysTick to make this happen every half a second so that your LEDs will update every half a second. Or maybe you want to do this every whatever time frame you want. But now, as you change the input, at some point in time, the output will update. So you don't have to do it at processor speed. You can slow it down, use SysTick to generate a scheduler for you. And step 4 here, it says use the Scopy voltmeter to measure the actual analog voltages. When I show you the Scopy screen, you'll see you probably don't even have to do that. Okay, so that's what you have to do. You have to take channel 4 or PA4, set it up as an analog input, do conversions on it, display the result of the conversions within these 4 bins out on your LEDs. You're going to post a short video of this all in operation. So you need to display the voltage that you're applying as well as the display that's appearing on your LEDs. And you're going to increase and decrease the applied voltage within its range, showing that things are working, that changes are occurring. And then just post the link to the video in the assignment link that I've provided. This last part of the lab handout is just a recap of pretty much stuff I've already said. So your A to D initialization routine, you're going to turn on clocks for ADC1, AFIO, and port A. If you've got your LED, and remember, this is just your ADC initialization. If you're using the LEDs as output devices, you have to initialize them as well. They're not specific to the ADC, so I haven't talked about them in here. This is just the ADC. So turn on ADC1, the clocks are ADC1, AFIO, and port A, because we're using PA4. Make sure you've configured PA4 as an analog input. Go look in the manual under GPIO X CRL, and you'll see that in order to create an analog input, you have to have zeros in the mode bits and zeros in the configuration bits. You want to do that for PA4. And then turn on the ADC, and that's just by writing the AD on bit into ADC1 CR2. So there actually is a mask called ADC CR2 AD on or something like that you could use. All right. Then your function to actually read an analog value, you could write this function in a couple of different ways. In today's lab, we're only using channel 4. So the first thing that you could do is when you call this function, you could just write a 4 into the sequence register because we're only ever using 84. Now, if you're using analog signals in your project, you probably have more than one analog sensor. So what you need to do is get the value from one analog input, then go back and get the value from another analog input. Like I say, we're gonna set this up to do it in sort of the simplest possible way. So what you could do is your function, you could pass an argument. You could give it the channel number as the argument that you're passing in. So you're gonna take that argument and you're gonna use it to write the value into sequence register 3, into the SQ1 bits. So decide what channel you want. After you've done that, write a 1 into the AD on bit of configuration register 2. That will start the conversion. Then make a while loop, which is waiting for the EOC bit to go high. When the EOC bit goes high, then go read the value from your data register and return that value back to your main function. And that's it. That's the whole thing that has to happen. Now, there's 2 other things that I would like to mention. And the first thing is on Scopy. So let's bring up a Scopy screen. And while that's happening, I'm just going to run and grab my iPad. I'll be right back. Yeah, the trip from my lab to my office is a lot shorter here than it actually is at work. Okay, so if we were running Scopy and we've connected up to our ADALM, when we're going to be using the power supply output today, so that's the V plus output, and that's here in our power supply tab. So if you click on power supply, it'll open up the control panel for 2 signals. Up here is V plus and this is V minus. We're not using V minus, it's our negative power supply. So that's the white wire. It's not connected to anything. I'm even sorry I mentioned it. So this is the red wire. This is V plus. And right here, notice it says V plus set equals 2.5 and then it says VDC measure. They're not the same. And that's because we don't have the power supply turned on right now. I don't want to turn the power supply on quite yet. I want to show you how you adjust the power supply. When you turn yours on, probably by default, it's going to be sitting at 0. You can decrease its value with the minus sign over here. You can use the little control over here in order to increase and decrease it. Or you can actually just type the value that you want right into this entry box, and you can see it'll change the set value. So I would actually type in the value that you want. And the reason that I would do that is that if you're using the plus key, it's really quite easy to make your voltage go over 3.3 quickly without thinking about it. And if you use the knob, it's also easy to get that voltage outside your allowable range quickly without thinking about it. But if you're typing things in, you've at least got the ability to type it in, look at it, and go, that's wrong, before you hit enter. So it makes it a lot harder to screw things up. Now, when you enable it, that's when it will actually start generating the voltage at the output. And you can see now, this guy has started changing a little bit. We've asked for 3.3. It's giving us 3.26. That's as good as it gets. Don't play around with the nominal voltage here, trying to get the measured voltage, right? Just set a nominal voltage and make note of what the actual measured voltage is. This is the voltage that it thinks it's applying onto your PA4 pin. So that's what you're converting, right? You asked for 3.3, it gave you 3.26. Go with the 3.26, okay? So now if you want to change that, what I would do is I would turn the power supply off. So go to disable, and I would make it lower. So let's say we want to go down to 2.5. And then when we enable it, you'll see that again, now it's measuring. We asked for 2.5, it's giving us 2.47. Close enough, work with the value that it's giving you, don't mess around, okay? All right, and then disable it before you change it again. So that's how you're gonna generate your voltages between 0 and 3.3. And you can pick whatever steps you want to make sure that you get results within your 4 bins. All right, so that's that. And then the last thing that I wanna do is I just want to quickly go over I just want to quickly go over the concept of resolution. And we're just about there. All right. So, how do you know what the resolution of your A to D system is? Well, you should have seen this before, again, at the beginning of the lectures when Dr. Zhang talked about A to Ds, but we're going to recap it. To calculate the resolution in your A to D system, you need to know 2 things. You need to know what the full scale voltage of your system is. And you also need to know how many bits there are in your A to D converter system. So according to that resolution, our equation would be V full scale over 2 to the n minus 1, where n is the number of bits in our system. So then, carrying that on, our full scale voltage is 3.3 volts. Our input range is from 0 to 3.3. So full scale of 3.3, and we have 12 bits in our converter, so that's 2 to the 12th minus 1. Which is going to give us 3.3 divided by 4095. That results in what we call a resolution, or a converter resolution, of 806 microvolts per bit. You're getting a 12-bit binary number. Every time the least significant bit goes up or down by 1, what we're doing is we're seeing a change in our input voltage of 806 microvolts. So that's your resolution. The value that you're reading, the 12-bit value, is just the number of 806 microvolt increments that there are in your actual input voltage. That's what you're seeing. And that's what section B is showing you, is the value that you read from the data register is a 12-bit binary number. And that 12-bit binary number is just your input voltage in volts divided by 806 microvolts per bit. So you're getting some number of bit changes, okay? Some number of least significant bits. You want to look at it that way. So for instance, our full scale is 3.3 volts. FFF would be equivalent to 3.3 volts. Now there's a little bit of error in there, because there's a half step that's applied at the beginning of our conversion range. We're not going to worry about that. If we see FFF, it's close enough to 3.3. If we see 7FF, that's halfway, that's going to be roughly 1.65 volts. If we were to see 3FF, that's a quarter of the way, that's going to be what, about 0.82 some volts. Okay, so you can the number that you're going to get from ADC1, it's being returned to you either as a 32-bit int or a 16-bit int, depending on how you set your function up. You can treat it as a decimal number, so you can compare it to 4095, you compare it to 2047. You can treat it as a hex number. You can do comparisons to FFF or 7FF. However you want to deal with it is up to you. Whatever number system you want to use is great. But that, again, is the recap of resolution. Okay. And that brings me to the end of analog to digital conversion. So next week, we will do one more lab, and that lab will be how to generate pulse width modulated signals using your timer system. That will give you the ability to do speed control or speed and direction control, depending on what type of motor or motor driver system you're using. And that'll be the last piece of your robot puzzle, because really in the robot, we've asked for some analog sensors, which now you hopefully will be able to deal with. We've set some digital sensors, which we've been dealing with switches or on-off signals for a couple of weeks. You can use interrupts to do scheduling, and you'll be able to control your motors. In next week's lab, or next week's lab period, the other thing that will be happening is we will be doing the project checkpoint. So the project checkpoint, I will take each of you aside into individual breakout rooms, and you'll be able to show me what you have on hand for your components. So there's marks for having components on hand. There will be a mark awarded for having the documentation for your components. So even if you don't have them, even if they're just on order, as long as you have a complete organized set of documentation for the components, there'll be some marks to be gained there. And you'll need your connection diagram, a professionally drawn connection diagram showing how you are going to actually do the connections. So consider it a schematic of how you're actually going to do the connections from your various components to the microcontroller. You'll need to show pin numbers on the micro, so how are you going to provide certain things? And at this point, the only question that we've never really gone over is which pins will be providing our PWM. For those of you with a Nucleo board, the likelihood that your PWM will occur on timer, I want to say timer 3, channels 1 and 2, is fairly high. For those of you with a VL Discovery board, the likelihood that your timer will either be timer 1 or timer 4, channels 1 and 2, I think. So, but if you got a VL, we can always move those numbers around later on as we decide different things. But those would be the systems I would look at using. So on a VL Discovery, timer 1, channel 1 and 2, and on a Nucleo, timer 3, channel 1 and 2 for your motor control. So one for your left motor, one for your right motor. Okay. And that's that. So next week is free marks, and it's a one-time deal, right? It's next week. It's a deadline. It's a demonstration at that point in time. There's no extensions. There's no different day, except in extremely extenuating circumstances, right? But normal circumstances, just the fact that my stuff didn't come in, or my cat ate my files, or whatever. Yeah, it's a one-time deal. So free marks next week or not. Alrighty, and that's it for me. So I'm going to go quiet here, and feel free to send me messages in the chat or whatever. And good luck with analog to digital conversion.